My goal for today is to say, what is all this about? And the problem, with pedagogical introduction into the subject is that the way Strogat's book is organized is 1 dimension, 2 dimensions, 3 dimensions. Now, nobody in his right or her right mind would describe a subject like nonlinear dynamics by saying it's something that's in 1, 2, or 3 dimensions. That's not what is it about at all. There's just pedagogical approach, which I love. I think Strogat does a good job. And the other problem with the pedagogical course is that, it introduces a new body of knowledge for most people in a stepwise and, referring to what you already know kind of way, which is the right way to teach. But once you're done and you look back at it, it's just like a bunch of disconnected examples. What is this all about? Would you be able to summarize the course? So I don't know whether you'll be able to summarize the course, but I try to do it every time. It helps me at least get a better focus. So it's a little bit like preparing for comprehensive exams. What do I need to know on a scale of 1 hour about this subject to be able to reconstruct the rest? Many people think about non-linear systems. It's unavoidable in chemistry, engineering, physics, climate studies, biology, epidemiology, cardiac dynamics, all kinds of subjects, many, many subjects. We share a set of tools, all of us, in these subjects. And we emphasize different aspects because in research, different aspects become important. The people who do this seriously and only this, and they get salary and tenure and prizes and all kinds of things for it, they're mathematicians. What I will try to do is, I have a mathematician I admire. Her name is Lai-Sang. She's a professor at Courant Institute at New York University. And I think she says what the subject is quite clearly. So I try to just reproduce her, but I think it's too brutal, so I'll have to intervene and translate nevertheless. We two like twins. I mean, she's the twin in a bright light and I'm invisible twin. But the subject has its intrinsic necessity. So once you have to start dealing with this problem, it's a little bit like knowing mechanics and knowing electrodynamics at the end of 19th century. Somebody had to write down special relativity. It just has to be done. It's not optional. It's intrinsic to the disparate pieces of knowledge that you have. And the same thing is true of dynamical systems. I mean, eventually, this synthesis, the code version of it should be the same. So I'll try to follow her a little bit. And I'll try to follow another reputable mathematician, John Guckenheimer. I'll occasionally quote him, and I will quote her. Here is what John Guckenheimer has to say about dynamical system theories. So it's a theory, it's a geometrical theory ever since Poincaré formulated the way of thinking we are following here. And it's a qualitative theory. And it's a very extensive body of knowledge because we have been at it for at least 150 years, maybe a couple hundred years. And it's a body of knowledge that has been accelerated in the last 50 years or 30 years by advent of computers that made many things possible that are not accessible to people who, don't have the depth of Poincaré or some other, deep thinking mathematicians. Guckenheimer says the logic of dynamical systems theory is subtle. One abandons Newtonian way of thinking of just writing all possible theories as differential equations or difference equations, etc. One has to realize that trying to write a theory of all things, in spite of some of my colleagues claiming using such words in what they call fundamental physics, in spite of that, it's hopeless and it's a fool's errand. You have to be selective. In mathematics, you might be able to go in any direction whatsoever because you're only guided by basically beauty and aesthetics. In description of natural world, you have to carefully restrict attention to phenomena that you care about. And there are two steps of this. You have to learn how to define the system of interest. And it is not very simple. You're taught this stuff in physiks because you're just given this book of knowledge as it's some God-given stuff. But, an incredible amount of pain went in putting together gravity, electrostatics, magnetism, electromagnetism, quantum theory, special relativity, general relativity. All of those things took a long, long time and much thinking to specify. So this is highly non-trivial thing. And this is what we tend to call physics, and maybe mathematicians call mathematics, but I think of it, that's what physicist does. And the other thing that a physicist has to do, he has to assign the importance to various aspects of the problem. So you have to describe, what is it that you have to observe. So you care about, you select from all possible things you could say, things that are relevant in understanding the principles, how it works. In this geometrical way of thinking, you are handed the law of nature in one or the other. So if you join a research professor that runs his own boutique at any university, you're kind of handed a particular law of nature that you find fascinating and you want to know what to do with it. So in theory of dynamical systems, and again, there's a totally different way to think about this, which is more statistical, mechanical. But what we described in this semester is you have to define a dynamical system, which means you have to describe, at least mathematically, exhaustively, precisely, a space in which an abstract point in that space is a possible state. So that's a state space. And then you have to describe the law. How does law act on this space? In dynamical systems, you tend to think it's evolution in time. But when I showed you period doubling renormalization, evolution was not actually in time, but it was, in renormalization time, which in that case happened to be logarithm time. So it doesn't have to be time, but mostly you can think of it as time. Strategy, explore it, look at local properties. If you can find anything that's stationary, you're in good shape. Then you try to determine either equilibria / missing from this picture or fixed points. Then you try to simplify the other parts of the flow by sections, by cutting it across Poincaré sections, getting return maps. Then you try to explore what happens to the neighborhoods of points. For example, you have some privileged points which are either fixed or by the time you're done this, they're periodic points. And then you want to go into the whole space, explore it. The way to do this is to explore the neighborhoods by linearizing the flow and by computing linear stability of invariant things like equilibria, fixed points, and stability eigenvectors and eigendirections. Then there is one thing that lots of people rather would ignore, but you absolutely must ask yourself, does my system have a symmetry? If it does, and I can't emphasize it enough, people in quantum mechanics know this, but engineers not necessarily. You must use it. It's totally essential. Not using it would be stupid and embarrassing. So now you explore your space by looking in here, there, and in infinitesimal or in linear neighborhoods, small neighborhoods. You're not understanding all possible things, but you have to understand in some way and classify all possible behaviors of your system. This you do by going global. So one way to go global is to subdivide the state space into finite subvolumes, give them names, that's called symbolic dynamics, use your stability eigendirections and allow them to trace out stable and unstable manifolds, which now go into the global space and they connect things. They partition the state space in an invariant way. Now, invariant means that it's a geometrical or topological concept. It says that whatever you do, you will find qualitatively same partition because the stable, unstable manifolds are invariant properties of dynamics. They cannot be destroyed by just changing coordinates. At this point, introductory course in dynamics stops, and there are various options. I'm very prejudiced. I think there is only one option to proceed to learn dynamics, but this is a minority point of view. This is how I and Strogas taught you. Now, what does my colleague and wonderful communicator Lai-Sang, here is how she thinks about it. She says, well, this is chaotic. She takes two kind of perspectives. One she calls geometric viewpoint. She says the important thing is that system should be hyperbolic. By that she means something that we emphasized often. You have exponential divergence of neighbors. So everybody which at some time considers somebody else a close neighbor experiences that they are going not just away, but they're going exponentially, which is very fast with time. So that's called hyperbolicity in mathematics, and it can be done more precisely. And this was developed in steps. So Hadamard in 1900s thought of billiards not on a flat plane, but on a curved space of negative curvature. Negative curvature means precisely that all neighborhoods are separate. If curvature is positive, they kind of focus. If they're negative, they go away each other. Brothers Hopf, Hedelund in 1930s produced more examples of this behavior, and they're very intuitive. They constructed billiards and stuff like that, in which every time you hit a round edge, you defocus. So there are explicit examples. The modern point of view was formulated by Anosov in 1968. And Smale axiomatized this, so he turned it into reputable mathematics. Of course, these are all great mathematicians already. But his vision, which was the Smale horseshoes I tried to explain, from 1960s, is in mathematics literature called very uninformatively There are dynamical systems that satisfy axiom A. Could it be less helpful as a designation? And the idea is this, you have a state space that's a collection of points on continuum, so they have well-defined neighbors. And if you take any one of those points, you discover that there are directions in which you fall in, and there are directions in which you fall out. That's called hyperbolicity. If it was ellipticity, you would be kind of rotating or falling in every place. But in hyperbolic systems, you have some directions where you go out, some direction you go in. And this is now in arbitrary dimension. This is not in Strogat's 1, 2, 3 dimensions. The precise statement of this is that you say there is tangent space. When you look at this state space, you think of it as something like you think about in general relativity. It's something that's curvy every place because it's described by nonlinear laws. And nonlinear laws are not lines, but they are wiggles of various kinds, hopefully smooth. And at every point, because it's a smooth space, nicely behaved, you can imagine that you're in Atlanta and you can make a flat chart of state of Georgia locally. That's what's called tangent space. It means that at every point on this manifold, somebody has a local chart which is flat. They have it in Beijing, we have it here, they have it in Kyoto. And that, of course, has some name, T for tangent. And the way you think of it, it's called tangent bundle. You think of it, not only do you have space M, but for every state, there is a little linear neighborhood. They might teach you this when they teach you general relativity, special relativity. You say, locally have a little elevator or, some enclosed space where I can use my linear stick and measure things. That's a tangent space. And now in hyperbolic spaces, this divides into some, so tangent space at every point divides into some of the unstable or expanding directions and stable or contracting. So the blue guys here are the contracting one and the purple ones are expanding. So that's the first thing you need to say something is chaotic. It has to be every place hyperbolic. Now this statement, every place, makes it very, very tough to establish mathematically and makes the set of examples that satisfy this requirement, pretty small, okay, isolated points in a bigger world, which is world of all dynamical systems. These are very special ones where everybody loses neighbors and is hyperbolic. Now that by itself is not necessarily interesting because what would happen is that you could be in a situation where everybody runs away and doesn't come back. This is kind of pretty uninteresting world. Things fall apart and then nothing happens, right? That's not what we want to study here. So we think of physical kind of systems in which you cannot just have infinite energies burned, infinite viscosity. You get reined in if you try to run around. And here comes the second geometrical notion. It's now, a little bit more abstract, but it has a pictorial geometrical idea. So this word is inherited from statistical mechanics for good reasons, but it's not necessarily used in the same way as in statistical mechanics. And the idea is that when you have these dynamical systems, You might find that, for example, for Lorentz attractor, a generic point just runs around a Lorentz attractor that 2 years old, and it just runs around, so it does something. It goes do da do da do da do da do da do da do da. It produces the picture that you see every place of Lorentz attractor as an example. But then there are very special points. There are equilibria. They don't go anyplace. But then there are one-dimensional subsets of the space. For example, a thing that starts here, hops on the other side, comes back, hops back, and does this forever. So that's a set, that's an invariant set in time, doesn't change its shape. And if you happen to be a point on that set, you just march around it, but you never leave it. What you want when you talk about entropy, you have to establish that you have exponential growth, exponential in time, of distinguishable n orbits. So n equals 0, that is equilibria, they're definitely distinguishable. But when you start looking at periodic orbits, you discover that there is another orbit where you start a little bit closer to equilibrium, and you run around, and then you jump, and you come back. So you have an orbit that winds around twice and once on this side. And that's totally distinguishable from the other orbit. They're both isolated because they're unstable. So they're pushing each other as much as possible. And that's what you mean by distinguishable. Hyperbolicity, the local property, ensures this. But their number, when you start exploring them, grows exponentially, and their logarithm is called topological entropy.
What exactly is growing in the orbits? Is it like a way up and up?
Yeah, growth of orbits as a function of time. So as you go for longer and longer time, you find more and more orbits, which are, in this case, periodic orbits. And they're all distinct. They have nice names because this one stays around for 2 unit times if you had a Poincare section. So we call left, left, right. While the other one was called left, right, left, right, left, right. So each one of them has a name, and the number grows as a function of time, meaning the length of the orbit. As the orbits you're counting have longer and longer period, their number grows exponentially.
Okay, so if you put a Poincare section in through the orbit,
you would find more and more points as you go to longer and longer time. And we know this both from the simple one-dimensional maps. So we know this from Bernoulli map. We know when we go twice as long a time, we have twice as many points. And that happened to be also true of the folding maps, like the parabola, because you're allowed to bounce between left and right side. And at every step, you have choice of 2. So the number of orbits grows like 2 to the n, meaning that logarithm grows like n times a logarithm of 2. And this logarithm of 2 is the simplest example of topological entropy. Topological is used here to say that's a qualitative counting. It's different from entropy as defined in statistical mechanics. So one has to emphasize that it's a different kind of entropy. So that's what an intelligent mathematician who is human and who thinks about these things, it's not just a robot that proves theorems, that's how they think about the problem. But when they write it down quite differently, except Lai-Sang is honest. So she says, this is how I think, and this is what I write down. So what did I write down? That's called ergodic viewpoint, which means it's a mathematization of this geometry I just gave you. So turn into computation of numbers that you can establish exist and compute. So by hyperbolicity, then they say you must have positive Lyapunov. They say I have a Jacobian that's well defined, that's linearization of the flow. I'd start at some point, X at time 0, I'll drop the time. And I go, to make it simpler, I do it in discrete time, I go n discrete times forward. Now, a Jacobian is a matrix, and every matrix has eigenvalues and eigenvectors. So you can multiply this guy by an eigenvector. And what's the value of the eigenvector? A matrix evaluated an eigenvector is just a number. It's corresponding eigenvalue, of that matrix. And now you take absolute value of this, because this could have positive or negative sign. To take, but you're only interested in absolute distance. This is a distance of the neighbors along the eigen direction of this matrix. So you forget about sign. You take a logarithm, because this is going to go exponential in time. You divide it by n. You take a limit. N goes to infinity. And if you're mathematicians, it costs you nothing. If you try to do it, it's impossible. And you get a number which is called little lambda, because it's in exponent. If you looked at multipliers, eigenvalues of this matrix, I use big lambda, meaning these are the multipliers, but if you take their logarithms, they're the numbers. And because you're averaging this logarithm over time, this is expected to go to some sensible, number, which is for chaotic systems positive. And you have every number, you have d-dimensional matrix, so d eigenvectors. So you have different number for each eigenvector. So you have to specify it by which eigenvector you use. So this is eigenvector. Computationally, you can do it if you're clever enough. It takes some skill. So it's eigenvector of Jacobian matrix, linearized neighborhood, smooth neighborhood of a trajectory. And you get a set of Lyapunov exponents. There is a leading one. There is a next to leading one. And in generic case, they're distinct. And if there are some symmetries, their number might decrease, because symmetry might relay them. And that's ergodic viewpoint. It says that if I take at any generic point, not just some weird point like a fixed point, which requires infinite precision, just any generic x in the state space, if I compute its linear stability, which I can always do because I know how to do the law of motion. This is just integrating our matrix of velocity gradients. It's given analytically to me if I have the law of motion. I can extract set of numbers. Some of them could be positive, some of them could be negative. If they're all negative, it means everything falls in a point and you have a boring system, which is not even part of Strogatz, because it's dimension 0 rather than dimension 1. You fall into a fixed point. But if there is some number of them are locally expanding every place all the time, because you averaged over, to compute this, you average over all times, then you have a hyperbolic system. If some of them are marginal, you have to think extra, and some of them are negative. That's good, because the negative guys are falling in, so you don't have to worry about them. They're well behaved. And it's just like walking, dogs as a dog walker. You only have to worry about the dogs that are running away from you. They're described by the positive one. And if you're trying to walk cats, of course, all of them will try to run away from them. So that's the first stuff. Hyperbolistic neighbors disappear, turn into mathematics, ergodic theory. The second component is positive. entropy.
So the system is chaotic if at least one of the exponents of the Lyapunov exponents is positive,
Yeah,
right?
that's a necessary requirement. You know, you have to have at least some hyperbolicity. So it's perfectly okay that you're in million dimensions and there is only one unstable dimension. That's okay. Then the rest are stable. So you must have both expanding and contracting directions.
Okay.
And now the other one, so you see this is a computational thing, but if you're a skilled mathematician, you can put bounds on elements on these matrices, and you can establish something like normal, uniform hyperbolicity, proving that these guys are either positive or negative, but not zero. So there's a great deal of mathematics to do here. Now, for positive entropy, again, you're really thinking geometrically, because what you mean is that you can divide the space into union. So you have a high dimensional volume, and you divide it into a union of subvolumes. Each one of them, is a subvolume, and together they cover entire space. And then your idea is that entropy, in this case, should measure, how well, what's the accuracy I have or I need. So it's really quantifying uncertainty in location of the point you're interested in the state space, which is within one of these subvolumes. And size of this volume, so this is subvolume, you measure its size. So on unit line, it's a length. In a plane, like a known problem, it's an area. In 17 directions, this is 70 dimensional volume, but you know how to compute volumes. So you take a logarithm of this volume, just like you're taking logarithm here, and then you use the size of the volume as a probability. So you have divided, suppose that this space you define to have unit volume. Then these guys are small subvolumes, and if I throw a dart into this space, ending in a subvolume has to do with how big the subvolume is. If I assume by ergodicity that I'm likely to fall into every subvolume. So probability in ending in subvolume is m. So what you're doing is you're using this probability density to evaluate logarithm of the volume. Now, what's a logarithm of the volume? When you have a number, it's specified by some digits. And the logarithm of that number is really just the number of significant digits. So if this logarithm is larger than, or smaller, if you're looking at numbers that are smaller than 1, then this number really is counting how many digits you have of precision. What's the uncertainty in location of it. And this is the basis of entropy that you might have encountered as used in computer science and in use in math statistical mechanics, Shannon entropy. It's a precision that you can attain if you resolve the space in some subvolumes. So that's what this means. And now you average this over everybody. And you do this for every partition. So now this really becomes mathematics, because nobody can possibly do what these guys define. Meaning I slice volume in different ways. I decide to divide it in, milliliters, or I divide it, God knows what, by scissors or by some other, So different people do these things. And now you take increased partitions. So you have some prescription how to make it finer and finer, but make sure that you're looking at comparable volumes and not setting some volumes too small and others large. So that's non-trivial, okay? Then for each partition, you sum up over all subvolumes, this thing. And now you take a limit of this where this number, I don't know what to call it, but this is now a number of partitions, goes to infinity. Good luck to you, but that's what mathematics is. They're happy to define it, prove it, and go home and be happy. And then, everybody in class has a different partition. Then we're supposed to bring them together, and supremum, the largest number that we obtained from 17 people, 23 people or whatever in class doing it, that's called supremum. That's what this ergodic theory is called entropy. You have different ways of slicing the space into smaller volumes. That's called partition. There is Zach's partition and there is Maxwell's partition. There, everybody has his own partition. They haven't talked to each other. One says, I like to have some kind of spaghetti volumes. The other one likes to have balls of different sizes that overlap. The third one likes to put it on a hypercubic grid. The other one says, well, it's stupid. I want to only cover the attractor, throw it away, stuff. So these are different partitions. Every partition is disjoint. Every partition takes a volume and slices in disjoint spaces, and then keeps repeating this. So there are different levels. This n is roughly speaking the level of your partition. So last time I showed you a picture. That's an example of partition. This is your state space. And you have some scissors to cut this plane into 3 pieces. And you have an algorithm to says how to cut up each piece into 3 more pieces, etc. So that's an example of partition.
N is the number of
so this is n equals 1. No, n equals 1 is the level of the partition, and then you have to sum over all elements. N equals 2 is the second level of partition. So this is 3 subvolumes. This has 9 subvolumes. So roughly the number of subvolumes goes like 2 to the, or 3 to the n in this case. This is now 1, 2. So this is the first level of the partition. Then you go back to this. I want to divide M2 to something called M21, M22, M23 union of and by that I mean I had this partition of level 1, and now this will be level 2 of partition. So this is what this n is. For every partition, you evaluate this thing, and you keep going. And its geometrical intuition is that you're finding, what is the number of digits I need to specify x, which is in a typical volume. So, I have to do it in 6-digit precision, or I have to do it in 11-digit precision, or I have to go to Wolfram and get 120 digits precision to be able to specify a volume, right? So that's what this logarithm does. And this entropy is a measure of uncertainty if you're replacing x by the volume that it lives in, which is, finite precision. That's what you mean by finite precision. Okay, so now I tried to follow the introduction, overview of the subject by Lai-Sang. And, they always go crazy on you. So here is what happens. Next step. First 2 steps a kind of what you know, but next step is already unreadable. First, she has to say that the manifold you are on a Riemannian manifold. Good luck to you. Then she has to say, that as this arrow is your law, as you go from some volume in this Riemannian manifold, you get into a smaller volume. In other words, you're starting to build up an attractor. And if you do this many, many times, then you find yourself into something she calls capital lambda for some reason, which is attractor. And the volume that you started with, if you take too large a neighborhood in Riemannian manifold, you might run away. That would happen for example, in parabola. If I start outside of unit interval, iterations just run away. So I have to have a basin of attraction for my system. And this example, for example, unit interval is a basin because if I start within it, I stay within it, I'm in the basin. But if I wander off the edge, I get kicked away. So that's basin of attraction. And now, ideal dynamical picture, the romantic one that I presented so far, is that this process, when you iterate a long time, builds up natural invariant measure. I explained it in last lecture. That means that, for example, in a non-attractor right here, when you look at every point and bracketed by a finite area around it, you can cover it, the whole attractor, by little boxes, every neighborhood here, which tells you how much time of your total time you spend in that neighborhood. That's natural invariant measure. And then if all lambdas, all this Lyapunov exponents, which is as defined, if they're all negative, then you fall into the hole, or a periodic hole in this case. It could be periodic orbit or attractive fixed point. But if some of them are strictly positive, this is strictly negative, then blah, 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 and SRB means Sinner-Well-Bowen, but that's what I called it. And you get a picture like we got for Renon. And for dissipative, meaning contracting systems, you expect this picture. If you have a system that's not contracting, that's called Louisville or Hamiltonian system, then you get a description that I might teach you in statistical mechanics courses, which is called Louisville phase space, which you fill out totally. So this is hopeless. So unfortunately, I have to leave Lai-Sang and give you slightly more humane explanation what is to be done. Remember, you started with a law of nature. You had to analyze it. First thing, you have to really do what was just written here as some kind of supremum of anybody's partition. But you have to partition the state space in such a way that it actually accounts for all what is called orbits, this guy here. You partition in such a way that you can count all way of getting here from there. Then you have to learn how to count, which is elementary but not so simple, which is you have to learn how to enumerate all possible orbits. More importantly for physicists, not necessarily for mathematicians, you have to learn how to measure, because some of these ways could be very unimportant. So you have to find out, give a mathematical formula for importance of particular way of getting from here to there. Then you have to learn how this notion of importance or measure is being massaged by dynamics. In other words, you have to how to evolve this measure. Did it last time. And why are you doing all this? Because you're trying to make predictions for the system in which you have no control after rather short initial time because it's exponentially unstable. So you have to do things like that you do in probability theory. You have to compute averages of your observable. Here, a beautiful thing happens, which I couldn't give you sense for in the last lecture. But there is a short time, long time duality. You're familiar with such things from other branches of physics because you know what Fourier spectra do. If you have large wavelength features on your data set, they'll become very sharp in the dual space, in the Fourier space. They'll be like sharp frequency and stuff. And if you have very sharp features in your space, then in the Fourier space, they will contribute to all Fourier components. So Fourier theory is defined on a circle, that it just eigenmodes on a circle. And what I started explaining by defining these evolution operators, I'll come to that again, is that can be generalized to nonlinear problems. And it's kind of beautiful and deep. And the result of all that is you discover that you only have to compute short periods in time to compute averages for very long time. So it turns out, even though individual trajectories you cannot control, the theory teaches you how to describe not things that are just as long as Lepun of time, but they're infinite compared to it. So that's super cool. How do you do it? One of our students in our group has just experienced disaster, which I've experienced only 3 times within a month. Last month, I had 3 computers die on me, but his laptop died, so he cannot do anything, right? And I'm trying to tell him, this is beautiful because why don't you think? Because everybody just computes. The deep insight of chaos is that once you understand what you cannot do, and that's actually Karl Marx's notion of freedom. Freedom is knowing your boundaries. If you know your boundaries, you're free. In this case, it's very true. In this case, Lepun of horizon, how long can your stupid computer chug along until it's meaningless what it puts out? This actually forces you to think. And you realize that in such situation, you cannot predict individual trajectory. That's fool's errand. But what you can predict is the average value of observables of interest to you. If you have an observable, your law teaches you how to compute its time average. Because average is additive, compute this much of integral, divide by the time, then this individual pieces are additive. Whenever you have something additive, but your theory can be described in terms of matrices, you stick this into exponential, and this gives you multiplicative weights. So that was the trick number 1 to finding these evolution operators. And this way of thinking, which requires no computation and only requires thinking, says that when you go to the times beyond what's computable by computers, you have to rethink everything, and you have to introduce evolution operators. And the result is that you find out that infinite time averages can be computed from these evolution operators. So let's say a little bit more about that. So what it says is that while Newton told you or Laplace, in his famous claim, deterministic claim that if you give me all bodies and in the universe and give me precisely their position, I can see the future as in a mirror. We know that's a lie. You can't do that. You have to realize that all the calculations you're always doing, you're doing them to finite precision. The laws are finitely precise. The time progress of the law is noisy to some extent, and so on. So this is, this whole premise is totally false. You have to reformulate theory in terms of neighborhoods, not individual points. Because you have finite precision, always, you cannot compute, it's not possible to compute anything beyond some rather short time. And now what you have to do is you have to trade in, you go to your Salvation Army place and you give them your single state space point and they give you a measure. They give you a little fuzzy box of stuff. And now that thing is evolved linearly by an operator. So you started with, let's say, Newton's laws, which are, 7 degrees of freedom for some system interacting by gravity or whatever, totally nonlinear. So you started nonlinear. And now you have a linear system and you pay a price. It's linear, but it's an infinite dimensional space. So that's called, simplest example is Perron-Frobenius. There are very many of them. Quantum mechanics has analog called Heisenberg operator. So you can think of finite time evolution this way, or you can think in Newtonian way, and it turns out Newtonian way is very simple. It's just called continuity equation. That's how we constructed this operator. But I find this one just like usual differential equations. I don't know really how to solve this one, but this one makes lots of sense. Then you have to think, how do you specify various measures? How do you specify these little clouds of points? And that leads you to notion of natural measure, which is robust to at least weak noise. So you would like to have some specification of neighborhood, which is not very sensitive to the precision by which you're doing it. And you can think of your precision of calculation or specification as noise, as saying I know it only up to some precision. And now, if you have already had a course in quantum mechanics, this is pretty amazing. You started with classical dynamics and you ended up with something only thinking classically and only thinking about what you can do, which has the same structure as quantum mechanics. There is a deep difference that in quantum mechanics, here you're looking at things that you can think of as probability density, at least the leading eigenvalue of this operator as a probabilistic interpretation. In quantum mechanics, you're describing things which are square roots of these densities. They're called probability amplitude. But it turns out when you study semi-classical quantum mechanics, the leading behavior, these things are just one-to-one. You have to understand classical mechanics described here. So this is deep, things that look totally different. In one course, they teach you, there is a ladder leaning against the wall and there's some stupid force. In other course, they teach you, take the bracket, HI, some total voodoo, and amazingly, you get color of the lines of excited hydrogen or helium. But in this way of thinking, they're same story. You have to add up lots of paths, classical, or you have to add up lots of waves. That's quantum mechanical version. What has happened, the notion of individual deterministic trajectory loses meaning. That means nothing. But things that are very sharp, they're dual to time. So you have to go for a long time to get them sharp, just like in quantum mechanics. And these eigenvalues in quantum mechanics, they're, for example, called energy eigenvalues, values of Hamiltonian. In this context, there could be other things. They're called correlations and covariances and whatnot. So a deep unification of various things that happen, which is not at all obvious on a slide that I showed you while I say young. And, in more detail, if you have an observable, you would like to find, if I stick my thermometer into turbulent fluid and I wait, 15 minutes while it's churning on time scales of seconds, I'll get something. Now, if I carefully see what happens to individual cases, that's called integral of the observable, and time average is divided by time, it turns out that this object is the same thing as the eigenvalue derivative of the eigenvalues. This you might see a lot in thermodynamics and statistical mechanics. This, what's called S here, might be called Helmholtz free energy or some other such thing in thermodynamics. And its eigenvalue could be some observable like temperature, pressure, etc. But this is much more general and has very tangible meaning in chaotic systems. So you have evolution operator, it's linear, it has eigenvalues. The leading one gives you basically all the information that you need. Now, this thing is lots of work. I could not explain it in this course, and certainly Strogatz could not get any place close to explaining this. And then, just really amazing thing happens is you go through all this, you go through all formalism that looks like thermodynamics. And when you're done, you can remove the scaffolding. That's what we do in mathematics. We never tell you how we got to the result. And the result doesn't care that you used evolution operators, their eigenfunctions. Only it gives you explicit, exact formulas for expectation values. And that I cannot tell you how it happens now. Along the way, there are lots of dangers. So mathematicians hide it in this sleight of hand that makes them happy. So this horrible limit of all possible partitions, find the best one, supremum, and then you get the largest entropy. That nobody can do. So why do they do this? Because there are lots of pitfalls, and they are kind of pitfalls that you're not familiar with. If you are not careful how you define, a weird thing, a function space, what do you care about? Hilbert versus Borel versus whoever, favorite Polish mathematician. It turns out that you have to be very careful how you do this, and that makes it a non-trivial thing. I'm simplifying it for you. You can easily make errors, and if you just run it on a computer, it could be 50% likelihood they're just simply wrong because your calculation is not careful enough. So it is not simple stuff. There is a natural resolution to many of these problems, which we cannot do even in a second course. And that is that the problems that arise in this description of dynamical systems is you make an assumption that the law is perfect. You assume that you cannot specify the precision of initial data that leads to these diverging neighborhoods. But the way you now run it through a meat grinder, which is called your iteration of the map or your differential equations, it's assumed perfect. That can be true. And it's a miracle that it works pretty well assuming this. So what you actually have to use, you have no other choice if you're looking at stock market futures or flow of the sewage in New York City underground. Any one of these things, you have to look at stochastic flows, meaning noisy flows. A noisy flow has to be written slightly differently. So instead of writing velocity, you write the deterministic part times dt. If I now divide by dt, I get the usual evolution. This is deterministic thing that we have been studying so far. People who do stochastic stuff, they have a name for it. They call it drift. Sorry, I'm not sure this is coming through. Drift. That's this part here. But then this was done originally by Norbert Wiener at MIT in the 30s or so. And prodigy, but not of the fine Protestant stock, so was not allowed to work at Harvard. You have to add to this stepping something that you intuitively know, but mathematics has to be slightly careful. You have to add Brownian motion, slightly more precise statement what you mean by noise. This is weak compared to steps given by velocity, deterministic velocity field. Deterministic velocity field can give you, if there was no noise, it will give you unique trajectory. Starting at 0, you would add xt. But what the Brownian notion does, it kicks you at every infinitesimal step a little bit, and you find yourself going around like this. And that's called a stochastic or Langevin or other trajectory. So the correct theory of dynamical systems should be really random dynamical systems. Lai-Sang and I agree. And that gives us, a summary of this course in a very, very general sense. If you make observation from deterministic dynamical system, the chaos looks like it's noise. It looks random. We use Bernoulli map to describe flipping of a coin. So it resembles stochastic process. Now, there are all kinds of careful analysis that enable you to distinguish a stochasticity, random in your neuronal network from the deterministic part. In other words, there are many, many methods by now in which, given this kind of trajectories, you pull out deterministic component and you do experiments and are able to describe the stochastic component. For example, firing of individual neurons rather than average firings, stuff like that. And it turns out it looks like more work because you just put some extra stuff in. But these systems are nicer. I always say noise is your friend because determinism leads us inexorably into these horrific self-similar fractal structures, which you can never explore because they repeat themselves ad infinitum. But the noise wipes out fine structure. At some point you can't see it because noise wipes it, and this is a great help. If you use what you have learned in this course about the deterministic motion, if you have some detailed info about determinism, then a little bit of noise, that's called weak noise, enables you to go a long way. Things that I find most impressive are applications in describing the weather over the ocean and neglecting the little things that happen on the scale of individual small cloud, or in neuroscience, using millions of neurons and getting as though there was just a collective behavior of some nice nonlinear system. So that's current vision of the field. My time is up.